Since the dawn of humanity, we have gazed upon the stars, our eyes filled with wonder and curiosity, and wondered if we are alone in the universe. This question has sparked countless myths, stories, and scientific inquiries throughout the ages. This fundamental question has driven us to explore the cosmos, seeking answers in the vast expanse beyond our planet. Our journey into space is a testament to our relentless pursuit of knowledge. Among the celestial bodies that have captivated our imagination, Mars stands out as a beacon of possibility. Its proximity and intriguing features make it a prime candidate for exploration. Its rusty red surface, visible even to the naked eye, hints at a past potentially rich in water and perhaps even life. The allure of discovering signs of ancient life on Mars drives our scientific endeavors. To unlock the secrets held within Mars's ancient rocks and dusty plains, NASA has embarked on an ambitious endeavor, the Mars Sample Return Mission. This mission aims to collect and return samples from the Martian surface to Earth. This mission represents a pivotal moment in our exploration of the Red Planet. It is a complex and challenging task that requires the collaboration of scientists and engineers from around the world. For the first time, we aim to bring pristine Martian samples back to Earth, where they can be subjected to the full power of our scientific instruments and analytical techniques. These samples hold the key to unlocking Mars' secrets. The knowledge we gain from studying these samples could revolutionize our understanding of Mars, its history, and its potential to harbor life. Each sample is a piece of the puzzle that could reveal the planet's past. It is a mission of immense scientific value, with the potential to rewrite our understanding of our place in the cosmos. The findings could have profound implications for future space exploration. The quest to return samples from Mars is not merely a scientific endeavor, it is a testament to the indomitable human spirit, our insatiable curiosity, and our drive to explore the unknown, and our unwavering determination to push the boundaries of knowledge. This mission is a symbol of what we can achieve when we work together towards a common goal. It is a journey into the unknown, fraught with challenges and uncertainties, yet brimming with the promise of groundbreaking discoveries. Each step forward brings us closer to unraveling the mysteries of Mars. The Mars Sample Return Mission embodies the very essence of exploration, inspiring generations to come and reminding us that the universe holds endless mysteries waiting to be unraveled. It is a beacon of hope and inspiration for future explorers. As we embark on this extraordinary mission, we stand on the precipice of a new era of discovery. The potential for groundbreaking findings is immense. The secrets held within those Martian samples have the potential to reshape our understanding of life itself, offering insights into the conditions that may have supported life on Mars, and illuminate the path toward answering one of humanity's most profound questions. Are we alone? The journey to find the answer continues, driven by our unyielding quest for knowledge and discovery. The success of the Mars Sample Return Mission hinges on selecting the right location for sample collection. This critical decision will determine the quality and significance of the data we gather. After careful consideration, NASA scientists chose Jezero Crater as the prime target for the Perseverance rover, the robotic explorer tasked with collecting the Martian samples. This site was selected for its rich geological history and potential to reveal secrets of Mars's ancient environment. This decision was driven by Jezero's unique geological features, which offer a tantalizing glimpse into Mars's watery past and its potential for ancient life. The crater's landscape is a window into the planet's history, showcasing formations that have been preserved for billions of years. Billions of years ago, Jezero Crater was a bustling lake, fed by a network of rivers and streams. This ancient lakebed is a prime location to search for signs of past life, as it would have provided a stable environment for microbial life to thrive. The presence of water, a key ingredient for life as we know it, makes Jezero an ideal location to search for signs of past habitability. Water erosion marks and traces of ancient water flow are evident throughout the crater, painting a vivid picture of its wet history. The crater's ancient river delta, preserved in stunning detail, holds the promise of sedimentary rocks that could contain evidence of ancient microbial life. These rocks are like pages in a history book, waiting to be read by scientists. Furthermore, Jezero Crater boasts a diverse range of rock types, including clays, carbonates, and hydrated minerals. Each of these rock types can tell us something different about the environmental conditions that existed on Mars. These minerals form in the presence of water and could preserve organic molecules, the building blocks of life. The discovery of such molecules would be a groundbreaking step in our quest to understand the potential for life on Mars. By studying these rocks, scientists hope to gain insights into the chemical conditions that prevailed on early Mars and assess its potential to support life. The analysis of these samples will provide invaluable data that could reshape our understanding of the Red Planet. The selection of Jezero Crater as the landing site for the Perseverance rover underscores the mission's scientific objectives. It highlights the importance of this location in our ongoing exploration of Mars. It is a location that holds the potential to answer fundamental questions about Mars's past, its habitability, and the possibility of life beyond Earth. The data collected here could provide clues to whether life ever existed on Mars. The samples collected from Jezero Crater will serve as a time capsule, transporting us back to a bygone era in Martian history and unlocking the secrets of a planet that has captivated our imagination for centuries. These samples will be a treasure trove of information, offering a glimpse into the ancient past of Mars. The original plan for the Mars sample return mission was a marvel of engineering and interplanetary coordination. It involved a complex sequence of launches, landings, and rendezvous, all orchestrated to ensure the safe and timely return of the Martian samples to Earth. The plan called for a series of spacecraft, each playing a crucial role in this intricate ballet of robotic exploration. First, the Perseverance rover would collect and cache samples from the Martian surface. Then, a second lander, carrying a small rocket known as the Mars Ascent Vehicle, or MAV, would touch down near Perseverance. The rover would then transfer its precious cargo to the MAVI, which would blast off from Mars, carrying the samples into orbit around the Red Planet. Finally, a third spacecraft, orbiting Mars, would rendezvous with the MAV, capture the sample container, and ferry it back to Earth. While this plan was technically feasible, it came with a hefty price tag. The estimated cost of the mission soared to over $10 billion, raising concerns about its affordability and sustainability. Furthermore, the complexity of the mission introduced numerous points of potential failure, increasing the risk of delays or even mission failure. These factors prompted NASA to explore alternative approaches, seeking a more cost-effective and streamlined strategy for achieving the mission's scientific objectives. In response to the challenges associated with the original Mars sample return mission plan, NASA began exploring alternative strategies that could achieve the same scientific goals while reducing costs and complexity. The original plan, while ambitious, faced significant hurdles that necessitated a re-evaluation of the mission's design and execution. Two new approaches emerged as frontrunners, each offering a unique set of advantages and disadvantages. These alternatives were designed to address the specific issues identified in the original plan, providing more feasible pathways to achieving the mission's objectives. The first alternative involved simplifying the mission architecture by eliminating the need for a separate lander to deliver the MAV. This simplification aimed to reduce the overall mission complexity and potential points of failure. Instead, the MAV would be integrated into the same lander that carries the Perseverance rover to Mars. This integration would streamline the mission's logistics and potentially enhance the mission's success rate. This approach, known as the Fetch Rover concept, would streamline the mission by reducing the number of launches and landings required. Fewer launches and landings mean fewer opportunities for things to go wrong, thus increasing the mission's overall reliability. The second alternative proposed a more radical departure from the original plan. This innovative approach sought to leverage new technologies and methodologies to achieve the mission's goals. Instead of relying on a rover to collect and transfer samples to the MAV, this approach envisioned using helicopters, similar to the Ingenuity helicopter that accompanied Perseverance, to retrieve the cached samples and ferry them to the MAV. This method would utilize the helicopter's ability to traverse the Martian terrain more quickly and efficiently. This helicopter retrieval concept offered the advantage of greater flexibility and reach, allowing for the collection of samples from a wider area. The ability to cover more ground could potentially lead to a more diverse and scientifically valuable collection of samples. Both alternative strategies presented potential cost savings and reduced mission complexity compared to the original plan. These savings could be redirected to other critical aspects of the mission, enhancing its overall feasibility. However, they also introduced new challenges and uncertainties. Each approach came with its own set of technical and logistical hurdles that needed to be carefully considered and addressed. The Fetch rover concept would require a larger and more complex lander, while the helicopter retrieval concept relied on the untested ability of helicopters to operate reliably in the thin Martian atmosphere. These factors added layers of risk that NASA had to evaluate thoroughly. NASA carefully weighed the pros and cons of each approach, seeking the optimal balance between scientific return, cost, and risk. The decision-making process involved extensive analysis and simulations to ensure the chosen strategy would meet the mission's objectives effectively.